Today's video, I would like to share with you a very nice problem of Austrian Mathematical Olympiad 2009, question number 1. Here is the following information for all positive integers and strictly superior than 0. Okay, prove this statement. Okay, we have to prove 3 to the n squared is strictly superior than n factorial to the fourth. Okay, so before I prove this one, I'm going to prove this fact, because I'm going to use it as a tool. Okay, so let's start with this one first. Let's prove 3 to the n plus 1 strictly superior than n plus 1 to the fourth. Okay, so I'm going to use the induction hypothesis here. So for n equals to 1, I'm going to check the base case. We'll have 3 to the 3 strictly superior than 1 plus 1 equals 2. 2 to the fourth is 16, the fourth, which is true. Okay, it's correct. Suppose 2 to the n plus 1 strictly superior to n plus 1 to the fourth is true. Okay, I'm going to take this assumption and work on it. Okay, so in order to prove this one, we must prove this one. We must prove 2 to the n plus 1 strictly superior than n plus 2 to the fourth. Okay, this is our goal. If we prove this one, we done the whole thing. Okay, 2n plus 3, because I'm just simplifying this one. Okay, claim 3 to the n plus 1 strictly superior than n plus 1 to the fourth by going from this one to this one. So I'm going to multiply both sides by 3 square. Okay, to get it to it. So 3, I will have 3 square is multiplied by 3 to the n plus 1 strictly superior than n plus 1 to the fourth is multiplied by 3 square. Okay, so this one is giving us 3 to the 2n plus 3 strictly superior than 3 square is multiplied by n plus 1 to the fourth. Okay, so in order to prove this one, we must prove this term is strictly superior than this term, n plus 2 to the fourth. Okay, if you prove this one, if I'm proving this side, that's mean this term is strictly superior than this one. That's mean we get to this one. Okay, that's our goal. So we are going to start with this one. We're going to work on this one itself by simplifying all these things. Since we have these terms are positive, so I'm going to take the square root on both sides. So I will have 3 to the 2 is multiplied by n plus 1 to the fourth strictly superior than n plus 2 to the fourth. Okay, so by taking the square root on both sides, I will get 3 here. I will get n plus 1 square is strictly superior than n plus 2 quaternary square. I'm going to take the square root again. I will get square root of 3 is multiplied by n plus 1 is strictly superior than n plus 2. Okay, so by simplifying these terms, I will get square root of 3n plus square root of 3 strictly superior than n plus 2. Okay, by taking n to the left hand side of this inequality, I will get minus 1 factor n strictly superior than 2 minus square root of 3. Okay, by dividing both sides by square root of 3 minus 1, get n strictly superior than 2 minus square root of 3 is divided by square root of 3 minus 1. By rationalize this one by multiplying by conjugate, I will get 2 minus square root of 3 factor square root of 3 plus 1 is divided by 3 minus 1, which is 2. Okay, so we'll have n strictly superior than 2 square root of 3 plus 2 minus 3 minus square root of 3 is divided by 2. Okay, this one is giving us square root of 3 minus 1 is divided by 2. Okay, if you calculate this one, giving us this one is strictly superior than 0. And is strictly superior than 0. That's what we have in our condition. Okay, so that's mean we have proven this one. Okay, since we have proven this one, that's mean we have proven this one is strictly superior than this one. Since we have proven this one is strictly superior than this one, that's mean we have proven this one. Okay, now we have proven this fact now. So in order to prove this one, I'm going to apply induction hypothesis again on this one. For all n strictly superior than 0, we have n equal to 1. I'm going to replace n with the number 1 here. We'll get 3 to the 1 strictly superior than 1 to the 4th, which is true. True. Last claim, 3 to the n square is strictly superior than n factorial to the 4th. We are going to prove 3 to the n plus 1 to the 3 to the n plus 1 square is strictly superior than n plus 1 factorial to the 4th. Okay, this is our goal. If we will get here, if we get to this result, that's mean we have proven this one. Okay, so now, I'm going to work on this one. So I have 3 to the n square is strictly superior than n factorial to the 4th. So in order to pass from this one to this one, I'm going to multiply both sides by 3 to the 2n plus 1. We'll get 3 is multiplied by 3n square is multiplied by 3 to the n plus 1 strictly superior than a factorial to the 4th is multiplied by 3 to the n plus 1. Okay, I'm going to put these two together. I will have 3 to the n square plus 2n plus 1 strictly superior than n factorial to the 4th is multiplied by 3 to the n plus 1. Okay, so this one is a form quadratic binomial. This term is a n plus 1 quinary square. Okay, is a form quadratic binomial. So that's mean I'm almost there because this one is the same as this one. Okay, now I'm going to use this fact. Okay, this one, if you take a look carefully, 3 to the n plus 1 is strictly superior than n plus 1, the n plus 1 to the 4th. So this one is strictly superior than n plus 1 to the 4th is multiplied by n factorial to the 4th. Okay, I'm going to put this n factorial inside this one. Is giving me n plus 1 factorial to the 4th. Okay, so thus I have 3 to the n plus 1 quinary square is strictly superior than this term n plus 1 factorial to the 4th. Now I have proven this one. Okay, thus since I prove this one, that means I have proven this one. Thus 3 to the n square strictly superior than n factorial to the 4th for all integer strictly superior than 0. Okay, I have done with this proof. If you are interested in watching this one, don't forget to support us with your like and subscribe. Thank you for watching. I will see you in next video. Bye.